There are many ways to derive the acceleration time graph. One of the ways is to first sketch out the VT graph and from there derive the AT graph. We know that if an object is free falling through air, then the velocity time graph is just a straight line with gradients equals to g equals to 9.81 meter per second square. If an object is falling through a viscous liquid, then its velocity will not be increasing at a constant rate forever. Instead, it will be increasing at a decreasing rate as it approaches the terminal velocity. In this question, the object is actually free falling first before it enters the viscous liquid. So its velocity time graph will initially be a straight line graph until it enters the viscous liquid. Once it enters the viscous liquid, the velocity time graph is no longer a straight line graph, but a curve that approaches the terminal velocity. We know that the gradients of the velocity time graph gives the acceleration time graph. So while free falling, the acceleration time graph is just a horizontal line at acceleration equals to g equals to 9.81 meter per second square. Once it enters the liquid, the gradient of the VT graph is less than g, which means the acceleration upon entering the liquid immediately becomes less than g. The gradient of the VT graph approaches zero as the object approaches its terminal velocity. This means that the acceleration begins from a value that's less than g and approaches zero. You'll notice that this acceleration time graph doesn't appear in any of the options. So this could be the case where the object enters the liquid at a velocity that is higher than its terminal velocity. So the object will approach the terminal velocity from the other side instead. Again, the acceleration is constant when the object is still free falling through air. But notice that once inside the liquid, the gradient of the velocity time graph is negative, which means acceleration starts off being negative and slowly approaches zero. And that is the graph given in option B.